All right. I'm going to talk a little bit about our flagship project status, plans, and engagement. This has not just me, this is the contributions of 30 plus researchers in the center, graduate students, and it's really come together. And I'm really excited to talk about all the wonderful work that's going on. Let's see here. Advance. Why is it? Okay, it was advancing. Now it's not. Did I freeze up on you guys? No. Why is it not?
Seems to be trying to annotate the slide.
Yeah, okay, there we go. Flagship projects are significant investments by the center, really focused on policy-driven research priorities. Notionally, we spun Flagship 1 up over the last year. Flagship 2 is starting to spin up. Flagship 1 has been focused on spectrum awareness for coexistence. I'll talk a little bit more about that. And then Flagship 2 is really had some ongoing activity, but is really just starting to come together. So these are not tremendously long-term efforts unless they continue into a center renewal. But many of the things that we're doing are increasingly relevant. I keep seeing other projects and groups starting to do things that we've already started to tackle. So it's been kind of gratifying to see this come together. So right now there are, as I said, two flagship projects. We've got 30 plus researchers across the center engaged at the kind of senior PI level. They all have students and postdocs and undergrads that are working with them. And we've had 4 workshops to help put together and formulate flagships or to execute as part of them. There's been a whole effort to document flagships incrementally in research memos. This is really derived from the astronomy community, where you kind of put incremental, things that wouldn't be ready for a journal, but are important to the overall understanding of the projects into a memo form, and you write it down and get agreement with people on things. So that's been going quite well. We have a whole series of measurement platforms between the older Radio Hound and the newer mobile experiment platform we've put together. We've begun to get public GitHub repositories out with both software and soon to be hardware reference designs as open source. So this is really starting to put the work of the center out and make it available to the larger community. Flagship 1 is really what I would think of as being focused on the national spectrum strategy. We had to pick a particular aspect of the strategy to tackle, and what we did is we decided to focus on the 7 to 8.4 gigahertz band. This is because it overlaps with NOAA and NASA interests, which are kind of scientific interests, which fit well with many of the center participants' interests. And at the same time, we needed to build a lot of capability and infrastructure to enable kind of the sensing, awareness, and understanding of any band at scale. In this case, focusing on 7 to 8.4 gigahertz, but a lot of what we're doing goes well beyond that and is usable for scientific and technical investigations over a wider range of frequencies. So we really wanted to create a demonstration of what was possible for coexistence, and we wanted to combine this in a way that was exciting for students and really got them directly engaged. And so we focused Flagship 1 around a series of field experiments and campaign efforts to make measurements, to analyze those measurements, and to understand them in the context of policy and rights and economics. And so this is kind of uniquely broad. It also allows us to provide very unique experiences for the students in where we do these experiments, who they get to engage and interact with. We've had really great engagement from NTIA in both the teaching associated with our workshops on this effort, as well as engagement in the experiment planning. And we're going to be going out and making focus measurements I'll talk about in a second. And this is including both active and passive coexistence efforts. So there's both, we're going to be both transmitting signals in some cases, as well as doing, say, band surveys and others. And there's a lot of exciting work going on to build the infrastructure of spectrum awareness around this. So the experiments we're planning, we've done one of them actually. We had a student training workshop, which was about teaching senior undergrads and graduate students about our platform, about measurement for radio, propagation and sensing. There was a really great effort and time. People had a good time. We went around and had them hunt for signals. We used radio telescopes. It was dynamite. One of the things we did do is we actually got an FCC license, experimental license, thanks to Ira's team, to look and do active transmission in 7 to 8, 7 to about 7.4 gigahertz. And so that came through for us. And so we were actually doing some active transmissions as part of this early training workshop. We're now in very detailed planning for additional experiments. NTIA has some that they've brought to us, such as an East Coast propagation experiment they're planning for DoD. We're working with the Powder platform to look at coexistence waveform work. I think you heard some of that from Nikos yesterday about that effort. And then we're also looking at kind of extending that work with some of our mobile platforms here as a dry run in the early summer. Our big campaign this year is focused around the Very Large Array. I'll talk more about that in a second, and is slated for the week of July 7th. We're hoping to have a student data taking competition this summer. So for the students in the audience, we're planning on actual cash prizes to go with the student data taking competition. Won't be out of NSF dollars. It'll have to be out of other sponsors' dollars. So if you are a corporate sponsor and would like to sponsor a specific prize, I think we can talk to Nick about that in a little more detail. We'd be happy to leverage interest in that for the center and to make it a really good competition for our students. We've been talking a little bit to the NERDS folks about the Hat Creek experiment, MITRE's planning for the fall of 2025. And finally, we've got a real flagship class experiment. I think of this as kind of the almost the capstone experiment for this effort in spring of 2026, notionally with some NASA or NOAA facilities. It should be a really good demonstration of our full capabilities for measurement, AI, and analysis in this relevant 7 to 8 gigahertz band. A Very Large Array field experiment, it will be at the VLA this summer. We've been working with NRAO and NTIA to try to work out all the details of this. So for those who have faculty as part of SpectrumX and who have students who might like to be involved in this, please keep in touch with Mary Knapp about this. We're very much hoping to get a lot of students each doing a particular measurement targeted for that group of students, and to get them all in aggregate doing a really impressive experiment that explores the RFI, simulates 6G wireless, and looks at some approaches to more effective RFI mitigation for the VLA. And this is, of course, very important for the next generation VLA and future experiments. Now, we have a lot of work elements in Flagship 1, and I'm going to go through kind of some highlights. I'm not going to read every single thing off these slides. The slides have a format where we talk a little bit about the main idea in the upper left corner. There are some milestones that have been met, current ones that are being worked on, and upcoming ones in the lower left. You always have a nice graphic or visual in the upper right. And then we have the team involved in making this particular work element happen, as well as the key result. And I'm probably just going to read the key results at some level as I go through these and highlight them. The mobile experiment platform will get a little bit of a longer highlight here at the end, so I'm not going to go into detail, but we needed a platform for spectrum monitoring, propagation measurements, and coexistence experiments, and we wanted it to be out at the cutting edge of software radio, as well as usable in field experiments. And so those two things take a lot of effort to bring together. And we've had an incredible team led by Nick Rainville of Colorado, as well as a huge number of people here at MIT Haystack, and also our workshop students. We had at our workshop, our students helped build the prototypes for these systems and got first light. And we learned a lot from that effort in November that's gone into the 12 units that we're building and are about to deliver to SpectrumX members. So we really wanted this to be open. It's going to end up on GitHub, and it will be approachable for other people to replicate or utilize and leverage. Now, once you have a software platform, you want to control it. And so Notre Dame has been leading an effort to look at sensor control for this platform. This is really combining the best of what MIT and Notre Dame have done. Notre Dame had a lot of work on this for Radio Hound that we've leveraged. And this is all messaging-driven control and telemetry. And so that whole mobile experiment platform, we need a way to have scalable and distributed edge control so that we can control and monitor field experiments when systems are connected, and ultimately so that we can support the extension to much larger networks of lower cost sensors in the future. And so we've got a lot of ongoing work with this to develop the software stacks to make them uniform. All our mobile experiment platforms get installed with this, and it keeps the underlying control and telemetry and registration of the systems really automated. And down the road, we're planning on things like OpenZMS integration to make zone management a part of the transmission capabilities of the platform we're building. Now, once you have a platform, you're going to end up with lots of data and metadata. And so we have an effort to ensure high quality data and metadata. We're building on digital RF and SIG-MF, which are two formats for lower level data and metadata that the community has available to them. We're basically making these work fairly transparently with a thing called the Spectrum Data System I'll talk about in a second. And the idea underneath it, though, is that to really get long-term data reuse, to have experiment traceability, to have consistent analysis and processing tool APIs and interfaces, you really need to do a good job at this data and metadata layer. And extensibility is a key part of it. You need to be able to adapt to the future, and you don't know what future needs are going to be, but also just kind of being reasonably comprehensive. And, there's things to build on. SIG-MF has done a nice job. NTIA has done a great job extending SIG-MF in various ways and data standards. So we're looking at all of that and rolling it into a kind of clean integration into the MEP platform for data and metadata, so that there's good ways to take data, annotate experiments, and organize things so that they have long-term usability. We have a Spectrum data system that has been developed by Notre Dame Research Computing, along with input from a bunch of team members and a workshop that we held. This system was up and running as of November, having started in September. I got to say, the team at Notre Dame has done an unbelievable job standing this up. Underneath it, we're trying to produce a federated data system for spectrum experiments. Now, what does that mean? Federated means that you can have more than one of these instances or data systems running. You can run your own. You can run your own at your desktop or your lab. You could run it on a server. You can run it on a cloud with real infrastructure if you want to. We're going to be starting up one of these at MIT here shortly. Notre Dame has theirs stood up. We're expanding the capacity into the hundreds of terabyte range of storage. The system can handle low-level IQ spectrograms, and we're also working on the ability to upload analysis data products and annotate them traceably to the data from which they originate. So data gets ingested by the radios. Ultimately, some subset of that data ends up in the data system for a given experiment. You can search that. You can find data across experiments and across, ultimately, platforms that share metadata. And then you can get at that experimental data through simple APIs in Python or Jupyter Notebooks or other basically web-based pull of this information. And you can get it and do your analysis, but ultimately submit it back in a traceable manner. And this is really key to scientific traceability of spectrum analysis and measurement. And there's good authentication systems. There's good access control that's being developed. And so you can make the data you want to share available or keep some things internally if it's necessary. So the SDS has really come along and is actually usable. There's a link up there if you want to take a look yourself at the GitHub or run it yourself. Spectrum visualization interface is being built to run against the Spectrum data system. It's to provide seamless integration of cloud offloaded visualization, things like waterfall playback, visualization of data sets in various ways. We're working on digital RF integration at the moment and expanded visualization types. And then ultimately, this comes back to creating really good examples for users of how to use SDS to take data that's in the system, visualize it, analyze it for spectrum analysis purposes and scientific purposes, and ultimately get for the academics to publication. If you're not on the academic side, you may have other uses for something like this where you're just trying to visualize and understand what's going on in a spectrum environment. And this is the basis for building, for example, heat maps, waterfalls, IQ analysis, and really zooming in on the database from a user-friendly and easy to interact with point of view. Now, One of the things we have to deal with all this data is how to reduce the flow of that data. And I think this came up yesterday with our panel members. They were talking about edge AI as being critical to reducing data flows. And we've picked up on that ourselves, is that we really are working on edge AI algorithms to do what I call interesting things detection. Okay. And this is like the ultimate simplification of what Kong and team have been really digging into on here. But at some level, we want to be able to monitor and understand RF channels and then find things that are unexpected and capture them. And so you can think of it like looking through the viewfinder of a camera, but in this case, it's our mobile experiment platform. And when something interesting happens, you press the snapshot button and capture low-level raw data that allows you to analyze that event in more detail. And maybe the system can be automated to do that capture. So you could capture, every time a particular radar comes into a band that you're not expecting it in, or maybe the signals depart from Gaussianity, for example. So there's been quite a bit of work to look at various algorithms with cloud-based prototypes. We're going to be transitioning some of the better prototypes over to the edge to run on the Jetson platform, both to produce metadata in real time, as well as summarize the band we're looking at, as well as to produce triggering of the data system via control to allow us to exfiltrate less data into the data system that's more relevant, right? So it's about getting events or getting measurements that otherwise you might have to collect, say, a huge amount of IQ or a huge amount of spectrogram data. Here, we may be able to make that capture much, much more efficient ultimately. Now, to be relevant in 7 to 8 gigahertz means that we really have to be able to do coexistence experiments that look as if they are phased arrays based, all right? And we're not going to be able to duplicate exactly what the wireless carriers are going to implement or what, say, a Wi-Fi base station is going to implement. But nevertheless, we wanted a capability that allowed us to develop and implement interesting array techniques, both conventional techniques for spatial nulling, as well as more advanced techniques for adaptive beamforming or beacon following. Part of that is, led to an effort to develop an SDR testbed in a similar form factor to the MEP platform, but with a phased array for transmit and a phased array for receive. Layla at CU Boulder has been leading this with a whole team and a bunch of students. I'll show another slide because they've got such a cool group working on this. They have made tremendous progress on array hardware design, actual beamforming with some of the analog devices parts they're using, array antenna design. And so this is coming together into a capability we will use in our experiments to explore adaptive nulling. How well can we do to protect a radio telescope or a SATCOM system that might be interfered with in 7 to 8 gigahertz? It will help us also understand for the policy and rights side whether these are things that you could imagine requiring of systems deployed in this band so that their coexistence capabilities of the future really mesh better technologically with what's possible. So this has been going so well, I wanted to show this slide. This is their little phased array prototype with 4 elements there. You get these wonderful young students who's been working as a team on this flagship project research. And this has really gone, really well for us. And we're very happy with how well we've been able to integrate the students into this. And so the CU Boulder team's been doing a dynamite job on this. And we're really excited as the hardware starts to come together. Now, looking beyond our current generation of sensors, the area we've identified as having the most potential impact is to lower the space, weight, and power consumption of broadband spectrum sensors. And so this has led to what we call Radio Hound X, which is the next generation extension of Radio Hound. We're trying to do 100 megahertz to 18 gigahertz coverage in a ultra low swap architecture. We're going to have a couple conventional reference platforms to let us quantify performance improvements. And we're doing silicon ASIC integration for the tuner architecture and some of the signal processing and snapshot capabilities. We're targeting about 20 watts for Radio Hound X, and Radio Pup will be 5 watts. They're going to be proportionately smaller than the mobile experiment platform. And Sudhakar and team have been making a lot of progress on the tuner design, the analysis, and we're working together with them to try to get the reference platforms scoped out and hopefully integrated. I dare say it, by the fall meeting, we might actually see one of these living in the wild. The ASICs are going to take a little bit longer to tape out, but nevertheless, we expect to get down to really low power levels. 6 to 8 times improvement over the state-of-the-art systems is what we're really looking at. Um, Now, from a policy rights point of view, Flagship 1 is really digging in. We have a whole next generation wireless effort that is really about digging into the national spectrum strategy process, the issues involved, about facilitating dynamic markets, about looking at different spectrum sharing approaches. This area, we're going to ultimately get a report on and also engagement in this whole next generation wireless for 7 to 8 gigahertz. And hopefully engagement in some of the stakeholder meetings has been ongoing and will expand. And so there's been a lot of work by people on the policy and rights side to look at this. There are also some very specific projects going on in policy and rights. One is looking at dynamic spectrum sharing for 7 to 8 gigahertz. This is really about us experimentally evaluating and doing analysis along with understanding potential economics, policy, and rights impacts of various sharing approaches and mechanisms for 7 to 8.4 gigahertz. I keep hoping that I can get our team to come up with some really novel stuff that really is out of the box on this. But this engagement through this is also about defining things we can do in our experiments that we can go validate and test and compare to the theoretical predictions. In a similar vein, we've got quite a bit of work going on the design, modeling, and analysis of beacon signaling and coordination approaches. Mike Koenig likes to split this into not just beacons, but also into kind of pilot carriers. I think of this very differently, actually, coming at this from a different point of view. Is we're looking at this work from my point of view almost like hailing frequencies in Star Trek, right? You would come up to aliens that you'd never communicated with. I don't know, it could be the NTIA, it could be the FCC, and you want to be able to interact and communicate with them. So you want to self-organize your spectrum coordination so you can communicate efficiently and also not interfere with each other. And so that you want to look at methods to do this, maybe even self-organizing methods that are a very big contrast to a lot of the zone-based management or database management that's been ongoing. So we're really looking at this. We've got some very interesting ideas about combining beacon signaling with channel propagation measurement and also coexistence metadata transmission over wide areas. And this is all coming together into both theoretical analysis, hardware systems and signal processing to do the beacons, and then it'll fold into the experiments to actually experimentally be shown to work in the real world. So I'll be giving a little highlight about FP1 towards the end here, so I'm going to skip over this other than to say that this all comes together into an ecosystem. It's built around our students and their experiences. Data, we have a platform for it now. The platform is adaptable and extensible. We have software to support it. We have a data system to ingest the data and make it available to our researchers. We have examples already of visualization, and there'll be more extensive things as time goes on. And we have ways to coordinate all of this. And then, it's all about getting our team of people out in the field, learning experimental work, job shadowing NTIA as they do measurements so that they both get engagement with the federal agencies as well as learn best practices. And then also our next generation of radios to really cram all these things into the chips and to make the spectrum sensor box that you see up in the upper left ultimately disappear into the connector on the antenna. That's really where we're headed. Now, there's lots that goes with that. I'm going to shift gears for a second to Flagship 2. Flagship 2 has taken us a little longer to spin up than I'd hoped. And I apologize to people for that, but there's kind of limits to how fast we've been able to move and get resources in place. We are about to really spin this up at scale. And underneath it, we settled on scientific coexistence in the high frontier as what we would like to focus on for Flagship 2. And this is really about our ability to coexist in a very rapidly changing world of mega constellations. This is not just about Starlink. Starlink is one mega constellation. We're about to have Kuiper. There's probably of order 100 constellations that have been proposed, funded. Some of them have already gone bankrupt. And if you look at them, they range from everything from, optical measurement or, LiDAR measurement of the Earth through radio measurement, through communications, satellite constellations of various kinds. And of course, one of the big ones that's going to impact people's lives shortly is direct to cell phone. And what we're finding is that these sources of radio signals in the sky on these satellites are highly visible. They're visible for thousands and thousands of kilometers. And with satellite constellations already pushing 6, 7,000, satellites for Starlink, some other constellations are a little bit smaller right now. But with the idea that many of these constellations could grow to tens of thousands of satellites or potentially even more, we're looking at a future in a decade or two of 1 million satellites in orbit doing a whole variety of tasks for people that are actually very valuable. At the same time, we have scientific instrumentation that is often significantly more sensitive than communication systems. This usually is because we're using cryogenic receivers and designing systems to be sensitive all the way to the thermal noise level. And, while you might want to be able to do that in communication systems, it's usually cost prohibitive, to try to get a cryogenic amplifier in your cell phone, at least currently. On the other hand, we're often 4, 5, 6 orders of magnitude more sensitive than your typical communications ground terminal might be. This means that a lot of these satellite systems can potentially impact the data from radio telescopes or looking down from weather radiometers that allow us to do things like hurricane forecasting and tornado forecasting. And so we have some big gaps in dealing with the high frontier. We have a lack of prediction capability. We have really inadequate rights and coexistence mechanisms. It is the Wild West out there. What is going up with whatever people are feeling they need to do. And systems are being repurposed even on orbit to do new features and to expand the business model of the companies involved. And ultimately, even following which satellites are being launched is hard. Understanding their actual impacts on systems and weather models and weather forecasting, for example, is incredibly hard. And so the scale of these systems really matters. The fact that there's tens of thousands of emitters becoming globally visible, up to hundreds of thousands. And so we need to look at both the benefits and the challenges of these systems, how to interact with them in a cooperative manner, hopefully often, how to mitigate them where possible, and maybe understanding the aggregate effects of interference. So we've spun this up. We have a number of work elements. One of them is a modeling effort that's actually MIT has been doing quite a bit of early work on this. University of Colorado Boulder has some faculty who've been working in this area. And I know that we were talking to NTIA about some of the modeling efforts they've been doing and looking at how we might be able to merge these efforts into a coexistence simulator for things like radio telescope interactions with satellites. If you saw Sam's poster yesterday, we've actually done this quite extensively for Starlink and our Westford radio telescope. And this is extensible to other systems, but really building a platform and a tool that allows us to do this kind of understanding and visualization is going to be critical to Flagship 2. We're also going to look using those kinds of simulations at the scientific system coexistence and data impacts. So this is going to be both, what happens to astronomy as the sky gets bright? Well, it starts to be hard to see stuff is the answer. At a course level, we want to have a detailed understanding, an ability to predict as constellations get larger when we might hit a critical point where you need new technologies in a system like NGVLA in order to remain viable as a scientific instrument. That'll help planning, it'll help the design of the instrumentation as it scales up, and it'll also hopefully keep ground-based astronomy in existence going into the future. From a weather point of view, we're very concerned about looking down with the weather radiometers, not just at 5G on the ground, but at dynamically moving signal sources on satellite constellations, at the harmonics off these systems, which are not necessarily well controlled or beamformed in the directions you think they are. And so we're very interested in data denial as well as data biasing that might get into the information collected by, say, a system like ATMS or Tropics, for example, and what that does ultimately to the weather model predictions, right? It's not just about, look, we denied data, what percentage is lost? It's about, are you changing the predictions and the forecasts in meaningful ways? Finally, the other area with Flagship 2 is experimental characterization. This is an area that has been ongoing both at Colorado, although I need to give them more support for it, as well as here at MIT. We've been doing this with our Westford telescope, looking at Starlink and other mega constellations. So data collection is ongoing and is going to expand. We're really hoping to also tackle some of the propagation measurements and issues at the higher frequency end. And also look very much at the fundamentals, harmonics, and unintentional emissions of these systems, whether they're in protected bands or in bands that are critical, like weather radiometer bands or on the edges. We need to understand these systems and their impacts, feed that back into the modeling, and understand from the modeling, be able to forecast what a given system might do in the larger context of scientific coexistence. Finally, there's incentives, rights, and policies. These satellite constellations are a fact. They are in orbit. They are doing their thing. They are emitting signals. And in some cases, I will say they are emitting signals that were unexpected or out of band. We are going to have to live with this and understand how to deal with this within the ITU process, within the governmental process. Can we get market mechanisms that help to enable standards for satellite vendors in the systems they put up, in the kinds of measurements done before a satellite is allowed to be launched? What about impacts on things that are already at scale? Do we just throw our hands up and give up? Or are there things we can do cooperatively with vendors to improve the situation enough that it's not a catastrophic impact, that it's a blended impact? Now, I will say you can always turn things off if only briefly. I know there's been some nice work at CU Boulder on taking and turning off 5G signal base stations when weather radiometers go over briefly. The station is off for all of 8 seconds. The user doesn't see the end, interruption in data transmission, and yet the scientific measurement isn't corrupted. So there's a lot of things that can be done in a cooperative sense if people are willing to work together. And having open data, open approaches, open analysis is going to be key for a trustworthy process that lets us work together with people. Highlight for Flagship 2, this is our Starlink modeling and measurement work at the Westford Radio Telescope. The central picture there's actually a movie of Starlink and all its emissions and its side lobes, with a lot of assumptions, granted, going into it. And this is what you'd see as if monitoring the sky. We're actually quite interested in our ability to monitor mega constellations and understand when and what satellites are operating properly or are malfunctioning. And so there's a lot of really interesting work in this area. We've already collected more than 14 terabytes of data that's ultimately going to make it into our data system. So we're collecting quite the low-level data set to analyze these issues. Now, I'm going to switch over here to a separate movie here on our mobile experiment platform. This was put together by my team here at Haystack. I kind of told them what to do at the last minute. They really worked their butts off. It is by no means a perfect production, and my communications officer would like you to know that she can do a much better job if I give her more than a day. All right. But we threw this together, and I hope you guys enjoy it.
So for the MEP design, the mechanical design, we wanted to make it travel friendly, pretty much open source, as well as weather proofing it. So keeping it ready for rugged conditions. So we went with a Pelican case, and we also got one with travel wheels. We went with this design, this basically shape, very long and flat. So when we're integrating the components into it and working on it, you can see it all on one plane rather than having to dig through multiple layers. Another feature is having these carrying handles, so it makes it easy to pick it up on either side and also here. As well as this is where it basically opens up, just like this. So this is the bottom side of the Pelican case. Right now we just have an aluminum sheet metal laser cut piece. This will be for the traveling, just so nothing on the bottom gets hit or damaged. and there's just going to be 4 screws. So you pop that off, and this is where you see how every digital RF connection is going to make its way out of the box, as well as input power and the thermal exits. So what we did is we cut a hole in the bottom, and this is basically so we can recess these heat sinks so this could all lay flat if needed. What we have here are basically for the RF sock board and the Jetson assembly, we have 2 heat sinks, and what this is doing is it sends all the heat to this vapor chamber, and then with these fins we're doing passive thermal control. So basically this will be lifted up with legs, or wherever it is mounted, it's going to have some passive airflow through these fins. So we also have these bulkhead connectors, which you can see are weatherproofed and are gasketed, so this will stop any water from getting in. These are also gasketed, so you can see that they're hidden under this lip, but there's a silicone gasket, again weatherproofing. And then along this lift plate, we put these in to recess this down, allowing this to be flat. And we have some silicone sprayed in there, as well as neoprene tape. Depending on where these are going, depending on the experiment, more silicone can be added to make it even more waterproofed. That way, if it's mounted on its side and water rains sideways, you'll be protected. So, now if we take a look in the interior, you can see this is where all the guts are. What we did is we put 3 modular plates that were laser cut installed, so that way when things evolve or we want to change components inside, it would make it as easy as just ordering 1 new laser cut plate and reassembling it and popping it in. Another modular open source kind of thing we wanted is to have a DIN rail, so all of these components up here are attached on a DIN rail. That way, if you need to move things around or put in new components, it's again very easy to install in the field, and it makes it all flat and you can see everything. So to start off, on the left side, this is where our RF signal's coming in. We have here the RF SMA ports that lead out to the outside, and then here's the analog front end board. On the DIN rail, we have the wide tuner board assembly, and then that is all for basically this left side where we want to isolate all the RF signals. If we jump to the middle, this is where our RF sock 4x2 is, and it's inside this metal enclosure to help protect, to help shield it. So you can see all of our connections are coming out the side, but it's hidden underneath here. And then the last plate here, this is again a hidden assembly, but the Jetson board is in here, as long as the carrier board it's mounted on and the network card. So this is where the network card is, and it's on a half bracket. Basically, if you ever want to put in another network card, it'll make it as easy as popping the side off, slipping in the new card, and closing it. So that makes it pretty good for when we inevitably evolve to the next stages. So this is just to show the rolling functionality. You can see it's fairly light, and if it's a little bit too heavy, you can just stand with it and roll it.
We're here in the control room for the Westford 18.3 meter telescope. We brought our MEP to hook up. So we're going to walk you through how the RF signal gets into the computer for processing. So we have the signal coming from over here, from the telescope. All right, so we have our signal coming in from the Westford radio telescope on this coaxial cable, and it's getting mixed with our tuner to bring it down to a frequency that our radio can sample. So this tuner will send out a signal so that we can tune between 7 to 8 gigahertz, and then it gets mixed and comes in to our radio over here. This is the analog front end, and this accepts 4 channels for receive, 2 channels for transmit, and we have the ability to put in filters if we need it, and we can also inject calibration signals. And then it comes through this board and goes into our radio, which takes those 4 receive channels, 2 transmit channels, and samples them at gigahertz level sampling. And then that comes through into our Jetson computer, which has the GPU to do processing so that we can to handle these wide bandwidths of data and do all the kinds of processing that we need to analyze look for the spectrum and record the IQ data and record it at high sample rates. So we should be expecting that to come in at about 6.67 gigahertz, something like that. So yeah, we can see some RFI coming in from the motors to move the antenna. It looks like that went away, and yes, here it is. Here's the maser popping up at about the frequency we expected. Let's zoom in on the spectrum a little bit there. You can see it popping up above the noise. Let's zoom in. And this maser has a characteristic kind of 3 peaks, which we see here, so that's good confirmation that we're seeing what we expected. And yeah, so a successful test for the MEP to see a signal up in the near 7 gigahertz range.
So, that's the mobile experiment platform. I'd like to thank Nancy Coterie and the entire team that you saw there, who really did an amazing job on short notice when I said to them, hey, I really want to have a video for this. And Mary Knapp, who really, she helped get a lot of that organized and prevented me from being too ambitious and taking too much risks in the demo. But nevertheless, we really do have these things put together. We've got 12 of them that are in final, really mostly software testing and RF testing at this point. There's a few of them that need a little more assembly work, and we're going to be getting them out shortly. Probably, I think as soon as next week, we're going to start shipping them to Colorado and Notre Dame. We're hoping to get some of the firmware and software a little farther along before other SpectrumX partners get this. And then I think probably in a few probably a month or two, we'll start to be able to get the GitHub up with the documentation associated with this entire platform. You can order everything from Send, Cut, Send. The analog front end from Circuit Hub is a little bit harder to probably purchase. We may have to coordinate build runs of that. But nevertheless, the idea is to build a platform. Now, I'll also say that data that gets taken, we have a very simple way of uploading it directly with keys into the SDS, the Spectrum Data System. And so delivering data off these platforms into the data system for scientific analysis is really straightforward. And we're just at the beginnings of the capabilities that this platform allows. The radios are about the best thing we could possibly do in this type of form factor and size. The back-end AI ML computer has tremendous capability and processing power. We're handling hundreds of megahertz of bandwidth into the GPUs. And, ultimately, there's kind of thermal limits in some situations that we may run into. But I'm really very happy with the entire team and the ecosystem we've built up to be able to do the experiments that we're aiming for over the next year. So it's really exciting. If you want to get engaged, there's GitHub. There's all this stuff is starting to be online as open source. You can use it or contribute to it, so it doesn't have to be our platform. The student data taking competition is going to be really, really interesting and suggest an experiment. Faculty may have things they've always wanted to explore. The MEP's really, the tuner we put there can be modified to cover other frequencies quite easily. The phase lock loop on there goes up to about 22 gigahertz, and the mixer goes up to about 12. So there's a range of frequencies if you don't start changing the analog components, but you're a few mini circuits parts away from pretty much any frequency band you want to put into this. And we're digitizing, at multiple gigasamples per second with RF SOC. So there's a lot of signal processing capability that can be exploited down the road. I'm very excited about the flagship projects, as you probably noticed. If you have questions, I think now's the time. So thank you. We got about 10 minutes for questions here.
Thank you, Frank. So, folks in the audience, you're welcome to drop questions in the chat window, raise your hands. Go ahead, Federico.
Hi, thank you very much for the beautiful presentation. I love the video and also the demonstration of the rolling. Wanted just to ask about the GitHub and if you have open data accessible.
So the GitHub for the control software and the Spectrum data system are currently up and available, as well as the Spectrum visualization interface. The GitHubs that are going to be associated with the mobile experiment platform are in formulation still. We're making things work and getting it to the team right now. There's going to be a point where it becomes open. We are also planning on bringing in Mitch Burnett, who works with the Casper project, which is the radio astronomy signal processing project. And he's going to be doing a very advanced firmware for the 4x2 that integrates extremely well with both the astronomy tool sets for low-level development as well as with GNU Radio. So we're really targeting the ability of graduate students and senior undergrads to come in and innovate at the radio edge with these systems, but then to have this whole supporting ecosystem to get the data all the way back with metadata to the central data repository and for data analysis and research that can be shared across not just SpectrumX, but the larger Spectrum community.
Thanks.
We have a question about calibration here. We have a built-in calibration path on the units that can allow an external calibrator to be injected into each of the RF channels. We also have a loopback capability on the transmit channels to allow us to calibrate those channels. The external calibration that we will typically be doing, we're planning on shipping some of these units to NIST and have them go through the NIST process and calibration tools and actually get a NIST sticker on them for traceability. We will typically be doing hot and cold load calibration, but we do have RF switches on the front of the analog front end that are precision controllable either externally or by GPS. We can actually do things like every pulse per second switch a calibrator in for a millisecond. So it's very straightforward for us to do Dickey radiometers or other calibration approaches. Our larger team has a thing at Colorado. Part of the team has been developing a multi-channel cross-correlation radiometer approach. So I kind of think we will have a MEP that has one broadband channel that is instantaneously and continuously calibrated to radiometer performance levels. So we're very much aware and looking at how to calibrate this. All the oscillators on the unit are GNSS synchronized. It's an OCXO. It's an extremely good crystal. We have PPS alignment of the data that will be getting going here in the not too distant future. And so everything is kind of reasonably phase stable and calibrated. Now, as you go to high frequencies, you sometimes have to work harder to pull in that calibration and make it stable. So it's not that you might not have to do as much as with other platforms, but we've put the hooks and paths in to make it possible. It's not per se a built-in process. It's an analysis process you'd run on data with activities you'd conduct relative to the calibrators.
Emily, I hope you captured all those acronyms in that process. Good luck.
Sorry, I went all technical on you there.
Talk about acronym soup, man.
You guys haven't worked enough with DoD and NASA. I mean, come on, it's.
So let me jump in with a broader question. One thing that struck me at the MEP training workshop is that we essentially have a flash mob of students and researchers that we could call upon. At a certain point, we can call upon them to head out to the field and take some measurements. So in terms of maybe thinking ahead a little bit and adding that as a service that SpectrumX can offer to the community. Right now we're learning, we're coordinating, but eventually we'll have a certain amount of proficiency that we could say, hey, let's go take these measurements with these devices, everybody converge and get the job done. Mm-hmm. In your mind, Frank, roughly speaking, when might we hit that capability?
Well, it depends on what you want to do. I mean, from the point of data taking, we are looking for roughly June having another flash mob workshop, so to speak, but focused purely on knocking out the data taking for the experiment in July at the VLA, right? So, and there may be some predecessor work to that, with the powder platform. So I really think, Nick, at some level, it's like months to do that. Now, on the other hand, you have to plan this, you have to schedule it, so the process of this, Mary's been working since November to try to get the VLA experiment set up. And so it takes time to organize these things. I will say the flash mob we put together in November for the workshop and experiment there. That was we literally threw that together kind of in a month when you look at it. It was a lot of work. It was a lot of pressure on people that honestly, I got some feedback that please don't do that to us again, Frank. That was kind of really hard. But we brought the students in at the alpha stage. They really got this stuff initially assembled and working. Right now, did we go and clean things up? Yes, of course, we've gone in and cleaned things up, and we're still, there's going to be improving firmware and software for the next year. On the other hand, that was an incredible experience for many of those students. Now, we did pair it up with both us and NTIA lecturing on radio measurement, propagation, electromagnetics. There was a comprehensive kind of mini course to go with it. So I think that there's contexts where this works really, really well. And, I could see organizing something like that for different things, say ORAN or OpenZMS, or, I know that many of the power platforms do activities that look like these workshops. And many of them, I think, actually, I know the AirPaw one looked to be pretty big. They were having quite a few students. And, I'll say that the overlap of the people they had showing up and say SpectrumX could be better, right? So there could be joint activities with some of the power platforms where we show up not just with some students, but with some mobile platforms and some specific research goals to try to target via, whatever activity we go after.
Very good. It's very consistent with my thinking. Thank you, Frank. I think we might have room for one more question before we transition into our next session, which is the industry panel. No other question? Again, when are we going to get some MEPs at Notre Dame?
End of next week, maybe.
Okay.
Randy and Nick Rainville, I trust to do a little bit more of the checklist stuff that we might want to do. You don't want to even see our checklist for sending things out the door. It's long. I trust Randy and Nick Rainville to help us knock some of the bugs out, actually. Yeah, we're looking to ship very, very soon here. And the platforms have come along tremendously. So
we'll do an unboxing video when we get it.
all right.